Hi class, we are now on 16.8. This is finding equilibrium concentrations. So here's a chart to help you understand what the ice. In the previous section we've already done some of this, but we're going to tackle more of the complicated problems in this section. So here's a step. Prepare the ice table. Decide in which direction the reaction will proceed. Compare Q to K. Define the changes of all the substances in terms of X. Use the coefficient from the chemical equation as the coefficient of X. The X change is negative for materials on the side when the reaction is proceeding away, and plus for substances on the side where the reaction is proceeding forward. So basically, if the reactants are being used up, that's a negative, and if products are being formed, that's a positive. More simple than what that sentence says. And then solve for X. For second order equations, take square roots of both sides and use the quadratic formula. Or you can also simplify and approximate the answer for very large or small equilibrium constants. And this is what we're going to cover. Okay, so first of all, we have a reaction, just a generic reaction here. A produces 2 moles of B. We have an equilibrium 4.0. A reaction mixture at equilibrium contains the concentration of A is 1 molar. What is the concentration of B in the reaction? This is very simple because you would simply set it up. So we would set it up right here. We have a 2, so it goes to the second power. And then we plug in our numbers. So we have a molar, that's 1 molar for A, and we have an equilibrium constant that's 4. So we solve for B. So what we do is we end up getting this right here. We get a B squared, and now in the second it's B squared equals to 4. Well, we need to get the square out of here. So how do we do that? We put the square root on both sides. So remember, what you do to one side, you have to do to the other. So we do the square root. Once we do the square root, that will remove that 2 there and make it just with the concentration of B brackets. And then we do the square root of 4, which ends up giving us 2. So the concentration for B is 2, and that would be C. This is pretty much an easy, simplified version of what we're going to do in this section. Okay, so calculate the equilibrium concentrations of all 4 species given that the initial concentrations, we can see that CO and water are equal to the same concentrations, and then we have an equilibrium constant of 5.8. So first we just start by determining if the reaction will proceed to the right or to the left. So we calculate Q and compare it to QC. However, since there's only reactants present, so the only possible direction for the reaction is to proceed to the right. We don't have anything else to work with. So in this case, then calculate, so we set up an ice table. So as you can see, we set up the ice table with, what you do is you write out the reaction and then write everything underneath, initial, change, and equilibrium. Now, set in your initial reactants parts. This is with the Q. There's nothing here, so we have nothing to compare it to. And this is a 1 coefficient, so we -1, negative X. This is a 1, so negative X. This is a 1 plus X. This is a 1 plus X. So the coefficient, you would have to add the coefficients here if you needed to, but in this case, we don't need to. All right, so now let's go to the next part. And so we pull everything down. So whatever in these 2 sections here, we're going to pull down, and then pull down. So let's go to the next part. So now we set everything up. Okay, so let's set up the problem. And remember, we have, so what we're going to do is take the x's from everything that we have here. So here we have x and x, because we don't know what the change would be for the oh, sorry, this is this side. And then we're pulling down what we have for the reactants. So everything we're getting is straight from this point right here, right? All right, so now let's combine everything that we can combine. And as you can see here, we can square the x on top and we can square the equation on the bottom. And we make it equal to the equilibrium constant. So if you kind of ignore the rest of this on working, so now what we need to do is, in order to get rid of the squares, we do the square root to everything. Square root, square root, square root. When we do that, we get rid of the 2's and it leaves it with just this problem. And then we have the square root of 5/8. So we work that out, and x is 0.00088. Okay, so now that we have that, we can plug it back in. So we know now the concentration of our reactant, remember they're identical, is 0.0088 molar. So we're going to plug X in. We're going to plug this value in wherever X is, and we get the concentration for our reactants. Now, how do we want to make sure that it's correct? Plug everything back in, and we get 5.7. Our equilibrium constant is 5.8, so it's close enough that we are on the right track. Oh, I forgot to fix that title in front. Okay, so now we're going to do one that's a little bit more complicated. Okay, so on this one, at 1000 K, sorry, I was thinking of something else. At 1000 Kelvin, the equilibrium constant for partial pressure for the equilibrium below is 0.260. Determine the equilibrium partial pressures from these initial pressures. So we're given the initial pressures. We have our reactants. We calculate Q, which is exactly the same we would set it up for the equilibrium, and it gives us an 8. So this is larger than this, so this reaction is going to proceed to the left. All right, so now we can plug everything in. So we have plus X minus X. Why is that a big deal? Because normally you would put, remember, this is an equilibrium, but so you would normally do a negative X and a plus X, but this is one of the cases where the reaction is actually going towards the reactants. So this is where the plus X comes in and the minus X for the reactant. So remember, this is reaction. So normally we would do a negative and a plus, but because Q is telling us that everything's pointing towards reactants, we're flipping the signs. Okay, so now we pull everything down. We have it here, pull everything down. And we're going to now take the equilibrium constant and plug everything in with that. Based on, and the 2 is from the expression here. All right, so now let's solve for X. So we rearrange this into the general form of this. So when you have a square up here, but you don't have it at the bottom, you want to rearrange it. So basically you want to get everything, you do your best to get it all in one level and not with a numerator and a denominator. So we're going to work this out. So this is pulled apart, it's worked out on the top. And now we start moving everything to one side or the other to try to get it right here. So you're going to have to start remembering some of the math that you would have done in order to, some of this will start coming back to you hopefully, but we need to get it into this form. And that's the overall of here. So if it starts getting complicated, understand, remember this form and get it to this form. You have an X squared, we have an X, and then we have value that doesn't have it. Why? Because we're going to use the quadratic equation. See this right here? We're going to use this and plug everything into it. So when we have it in this form, this is A, this is B, and we don't have a C there. So here we go. We have a negative B with a plus minus square root. A B squared inside this square root is B squared minus 4AC. And let's plug that in. So yeah, this is C. Okay, so negative, we have a negative right here. B is 106, so you see the 106. Plus or minus B, which is 106. Minus, and it says 4A, A is 4. So here's the 4. So 4. And then C is 0.0387. 2A, which is 4. Plug all this in. You're going to get two values because you're going to get one that's positive here and one that's negative. It might change with this value here, but notice that this is how you're handling it with a positive and a negative, and that's going to change everything. But you should have two values. So what does that mean? This means this is 1.06 plus 0.710, and this is 1.06 minus 0.710, and then you divide it by 8. So you're going to have two values, and we have these two values right here. Once we get the two values, we're going to see which one works and which one doesn't. So basically, when we start plugging everything in, we realize that this one doesn't work. It's too large, and it yields a negative partial pressure, which we can't have. So this is what's going to happen. One's going to work, one's not going to work, in theory, if you did it right. So we can very easily determine that, okay, that didn't work. We plug in this value, and this is going to give us our values. So we end up plugging everything in. You can see here we got one value. Here's the other value. So then we can now plug it into our equilibrium constant with those values, and we can get what our excuse me, I'm getting tongue-tied here. Our final value, the equilibrium constant, is 0.262. The one that was given to us is 0.260. So we are on track. This makes sense. Okay, so now we're going to learn something different. Okay, so in certain cases, The quadratic equations can be simplified and don't require that whole quadratic formula. So wouldn't that be better if you didn't have to use that every time a problem got difficult? So this is a simplification, and it has to follow the criteria, which you still got to do some of the work in order to understand, but it does make things a little easier when you have to, if you don't want to have a more difficult problem, you want to try to make this as easy as possible, especially when it comes to math. Okay, so the simplification is useful when initial concentrations are large. So the initial concentration has to be a large amount, and the change in the concentration is relatively small. How would you know if these two conditions are met? Well, what would happen? What would prevent a change in concentration leading it to be relatively small? Well, the equilibrium constant would be small, less than 1. That means that when a reaction goes, it's going to mostly stay in reactants and not products, because of the fact that the equilibrium constant's very small. So not a lot's going to react towards products, and if you have a very large initial concentration, then you can pretty much ignore the X, is what this is saying. So the simplification is valid when the change in the amount, when we use a variable of X, 2X, etc., is less than 5% of the original amount. So that just means that normally we would have X, our initial concentration minus a coefficient and the X. We would just ignore this part. We would simplify, let's not say ignore, we would simplify this by simply, instead of doing the subtraction, we would just keep it with the original concentration amount. So then we would check our approximation. So if you weren't sure, you could do the X, and you would have to do that. So you have to solve for a portion of this for X, but you have to know that it has to meet certain conditions, so it's not for every problem. And then plug in that X value. So I took this from your reading. This was the X was solved for a problem. This was the molarity, the initial concentration molarity, so it's 1.0. Times it by 100, and this is the amount. So it has to be less than 5%. This is way below 5%. So this X could be ignored. So then go on to the problem. So here's a generic reaction. Consider each value of K and the initial concentration of A. For which set of values does the X is a small approximation most apply? So basically, given this criteria here, can you pick out one that we could follow the small approximation and discard that value X? And the answer is yes. Remember, I told you it has to meet two conditions. One, the equilibrium constant has to be small. It has to be less than 1. All of these here meet that, but B is a little larger than the ones with -5, and so is D. So those automatically I wouldn't pick, because we have values that are lower, smaller than them. So I would be looking at A and C. The next criteria was it has to have a large initial concentration. C does not have that, but A does. So then we can look here, and I was hoping I got this right. I forgot. A meets both criteria. So this could be one where you could solve for A, check the percentage, and then kick it out so that you could make this problem to solve it a little easier. So for this, again, everything here is just what I said. A small K value, initial reactant has to be relatively large. All right, so let's do a problem like that. So formic acid ionizes in water, and it gives us an equilibrium that is less than 1. So now we can take everything, plug it in to with our equilibrium constant. We have that here. So now determine the hydronium concentration at equilibrium if the initial concentration of formic acid is, formic acid is 0.250. So we're given some information here, and let's plug it in and see what happens. So here we have, there are no products present initially, so the reaction can proceed only in the forward direction. So we don't need to worry about Q. So in here, we're going to take this information. So we have our initial reactants. We have liquid water. So we're not paying attention to that. It's not involved in this equation. Minus X, because it's only one coefficient. And then this is one coefficient, so it'd be plus X. This is one coefficient, so plus X. So then we bring everything down, and let's plug it into our equilibrium constant with the concentrations. So we have X and X, and that makes X squared. Now we have 0.25x minus X, and in this case, we're going to remove this X. We're going to remove this bottom X, because what we're saying is that the equilibrium constant is very small. We have a large value of molar of initial reactant. So we're going to take a chance and remove it, because that makes this problem a lot easier. So dealing with this is much harder than dealing with this. So then once we plug everything in and we isolate for x and then square root everything, our x value is 6.71 times 10 to the negative 3. So that's a small amount. So now if we wanted to make sure that we were correct in removing the x on the bottom, plug it in. And you can see that the percent is 2.68. It is less than 5. So we were correct to remove it from our bottom equation, which is this one here. So because the value is less than 5%, the simplification works. Okay, so when sufficient information is given, the equilibrium constant expression can be used to calculate the concentration of reactants and products at equilibrium. ICE tables are useful to determining concentrations of species at equilibrium, and they're particularly useful when only the initial concentrations are given. And in some of these cases, that's all we can work with. When both reactants and products are initially present for a reversible reaction, then we need to determine their concentrations at equilibrium. We need to plug in Q because that's going to tell you the direction of the reaction. And as you can see with the other one, if you just went straight with not doing Q, where is it now? I don't remember. I think it's this one. Then you would have flipped those signs and this problem would have been wrong because we would have just taken it straight from the reaction, but you have to do Q in order to understand. In this case, remember, you have values on both sides, so you would have to determine Q. Most of the reactions that we deal with only have initial reactants and they don't have anything for product yet, so that's when you don't have to do Q. Okay, so hopefully this makes sense. And in some cases, you will need to use the quadratic equation to determine the concentrations. Write this down, make sure you have it. Some of these will get complicated. You need to be able to use this. You should be able to have the math skills to use this. Even if you haven't used it in a while, you should. There's a lot of problems, example problems in this section that you can, hopefully this makes sense to you. So when the initial concentration of reactants are large and the equilibrium constant is relatively small, that's when we can you can often simplify the equation expression to avoid. So that's when we do the simplification to avoid doing the quadratic. So this section was about the quadratic equation and simplification. And if you're able to do the simplification, that's wonderful because then you don't have to do that nice pretty formula that's right there. That's it.